So this is a huge statement, a very non-trivial statement. That means if you go back to our Poisson's equation example with the sine of pi x as the right hand side, we get the exact solution, not just when the right hand side is sine of x, but for a lot of different right hand sides, because I always minimize the energy norm, which is in Poisson's equation the norm of the derivative. All right. And of course, because we have the symmetric positive definite property, this A of E and E actually qualifies as a proper norm. So if I take the square root of A of EH qualifies as a norm, that's usually denoted as the energy norm of the error. And do we all know what a norm stands for function? Now, who knows what a norm means? Okay, a norm means so a particular we put a double column on this, qualifies as a norm. So it has to be from a particular space to a real numbers. It qualifies as a norm if first of all, my E is always greater than 0 unless E is 0, when this E has to be equal to 0. Okay. 2, it satisfies the triangular inequality, which means the norm of E1 plus the norm of E2 has to be less or equal to the norm of E1 plus E2. So it's just like the distance in a 2D or 3-dimensional space. It has to satisfy the triangular inequality. Okay. 3, it has to satisfy the kind of linearity under a scaling. So if you scale a particular E by a real number A, we always get the absolute value of A times E for any A being a real number. So if I have all of these 3 satisfied, then this double column can be called a norm. So in this case, we can show that if A is symmetric positive definite, the square root of that qualifies as a norm. And part of it is because of A is symmetric positive definite. Another part of it is coming from the fact that A is bilinear. It is linear with respect to both the first and second argument. All right. Okay, so we put this statement here. We haven't shown why that is the case. It's a very interesting fact that why a finite element analysis minimizes this energy norm. So let's take a look here. Okay, it minimizes the energy norm because of the following. So if you take A of EH and EH, okay, that by definition is equal to A of UH minus U, UH minus U, where UH is the finite element solution, where and restricted to the smaller space, and UH is within XH subspace of X, U is within the bigger space X. Okay, and now you expand this. How do we expand this? What property of A do we use to expand this? By linearity, exactly. So it is equal to UH UH, okay, minus 2 times A of UHU, okay, plus A of U and U, right? So that's a proper expansion of the bilinear form. So now let's start to take a look at that's not what I wanted to do. I'm sorry. That's not what I wanted to do. What I wanted to do is I want to show that this norm is the smallest, which means if I perturb this UH, if I change the UH to something else that is still within the smaller space, I cannot decrease this norm further, right? So that's not what I wanted to do. What I wanted to do is if I let UH goes to UH plus delta UH, okay, I cannot further decrease this A. So I want to do analysis on top of this perturbed UH. So this becomes UH plus delta UH minus U, and UH plus delta UH minus U, right? So this, I can get 2 terms out of this. One is A of UH minus U, UH minus U. And the second term is 2 times A of UH minus U and delta UH. And the third term is A of delta UH, delta UH. Right? This is again like the same expansion I was trying to do before, but instead of UH and U, I'm doing this with respect to UH minus U and delta UH. Is there this term we know has to be greater than 0 unless delta UH is 0, right? Because we have symmetric and it doesn't matter it's symmetric, we have positive definite in A. This derivation, this we can collapse 2 terms into this term is using symmetric property, but this we are using definite, positive definite property. Okay, so in order for me to show that the energy norm of the perturbed solution is greater than the energy norm of the error of the perturbed solution is greater than the energy norm of the error of the finite element solution, we only need to show that this term is what? Greater or equal to 0. Is it possible this term is always greater or equal to 0 for any delta H?
0.
This is basically saying what? I'm sorry?
0.
Yeah, this term, we need to show that this term has to equal to 0 for any delta UH, right? Because if this term is not 0, even if it's greater than 0, it doesn't work, because if I take the negative of this particular delta UH, I can make it negative, and that invalidates our the proof. So we need to show that this thing is exactly equal to 0 for any delta UH. And as you said, this goes back to the particular finite element statement we are trying to satisfy. What finite element we are trying to satisfy? We are trying to satisfy A of U. So let me first write down 2 things. Let me first write down the weak form of the exact PDE. So the weak form of the exact PDE is A of U and V plus L of V equal to 0 for any V in the bigger space, right? Right? And the finite element is A of UH and VH plus L of VH is equal to 0. Now for any VH in the smaller space, which is also part of the bigger space. Now I have a question for you. If I plug in VH into the first equation, would it still work? Yes, right? Yes, right? So if I plug VH into the first equation, because VH is within the smaller space, which is part of the bigger space. So VH is also part of the bigger space. That means if I use a VH, then both equations are satisfied, and the linear functional is the same. That means the A of U and VH is equal to A of UH and VH. Okay, when we go to find element solution, even though the UH is different from the exact solution U, but if you use a test function within the smaller space, within the finite dimensional space, the bilinear functional evaluates to the same value, no matter if you are using the exact solution or the finite element solution. Okay, that means A of U VH is exactly equal to A of UH VH, which through bilinearity means A of UH minus U VH is exactly equal to 0. Okay, so that gives me that, and then combined with the fact that A of delta UH and delta UH has to be greater than 0, it shows us that any perturbed solution is going to have a bigger error in the energy norm than the finite element solution. Or the finite element solution is the best possible within the particular XH for that. So going back to our incredibly accurate finite element example, this shows that my UH actually minimizes the integration 0 to 1 partial UH minus U partial X squared dx, right? So what UH minimizes that, and of course we can basically do integration by parts and figure that out. Well, let's just say, okay, so if we have a derivative of this, what partial derivative minimizes that the integral of that norm? So let's, for example, just integrate within a particular element. So xi plus 1, and I know that this thing has to be a constant, right? So that is a constant which can be pulled out of the integral. So this is integration of the constant squared minus 2, again this is the constant, times that non-constant plus a term that we have no control of. So we can control this thing to minimize that. Now if you take the derivative with respect to this constant here, let's say this is d, the derivative, let's say, and so this is the energy norm squared. So the derivative of the energy norm squared dd is equal to this is the square, so it's hi, the size of this element, times 2d, right, the first term, minus now this goes away, integration over the element of, again there is a 2 partial u partial x dx, which gives me the solution that d is equal to 1 over hi integration xi plus 1 partial u partial x dx. Or the derivative of the finite element solution should match the average derivative of the exact solution within the interval.